Welcome to our second workshop from Ajahn Sakol on the topic of getting the basics right, clarifying doubts about statistics. And I think it's just about time. So please take it away, Ajahn Sakol. สวัสดีครับ
สวัสดีครับ
ครับ
ขอบคุณครับ
ครับผม
Hello everyone. Thank you so much for coming. We have far fewer people, but hopefully, the class will still be interesting. So I'm pretty sure the class wasn't as interesting, but I will try and do my best this week again. Let me start with the PowerPoint.
Okay. So.
All right. So I'm sharing my screen, and let me make sure. Okay, there's before I start, it seems like there's a lag between what I have on my screen and what you can see on your screen. So hopefully things will improve, but right now it seems there's like a 1 second delay. So just so you know, if what I say doesn't really line up with what you see on the screen, wait for a little bit.
Okay.
So that's the first thing. Like I said, thanks so much for coming. This is the second class, right? The first class was last week, and we talked a little bit about research in general, right? And for the last hour of the class last week, I went into more detail. I went into statistical inference. I talked a little bit about what statistical inference is and some heavy concepts, right? Some difficult concepts like statistical inference, probability, and sampling distribution. And that's where we ended last week. I'd like to start class today by going back to the last hour of the class. And I have something to tell you. I knew I didn't do a good job last week for the last hour. So I decided to recap, and I am going to give you a little bit more information with new examples. And I've got to tell you, I'm very sorry. I knew it myself. It was a little bit confusing. I didn't do a good job explaining these concepts. So I like to start where we left off last week. The first part will be slightly shorter. I'm not going to spend an hour talking about the whole thing. What I wanted to do is to give you the main gist of statistical inference, to walk you through the idea again, and to stress why we need to know a little bit about probability, why probability distribution is important, so on and so forth. And then I'll tell you a little bit more about sampling distribution, what it means, what it actually means. Why do we actually need a sampling distribution? And then I'll go into some new materials. And today I'll be talking about significant testing, the p-value thing that you hear all the time. People say p-value of this, p-value of that. What is going on behind the scene? What's the process? What is significant testing? What is p-value, right? And the last part of the class today will be about statistical modeling, right? You may have heard this word before, and you think, whoa, it's complex, it's fancy. It turns out, almost everything we do in statistics class has to do with some kind of statistical modeling. So we are actually smart enough, right? We are good enough to learn about statistical modeling, even though we don't know that, t-test, ANOVA, and things like that are part of statistical models. So I'll walk you through some high-level conceptual ideas of statistical models. I'm not going to go into detail because this is not the right place to do it, and I don't want to overburden you with concepts that perhaps you may find foreign. But I want to talk about that because I feel it's the right place to do so, and it's a good place, if you want to get serious about learning statistics, having this concept is very important. Okay, so that's the outline of the class. Let me start again with a little bit of statistical inference, right? So I said last week, statistical inference is about making statements regarding an underlying probability distribution, right? We saw that underlying probability distribution of data. And I have a better example to clarify, to tell you what it means when we do conduct statistical inference. So, all right, we make statements about a probability distribution of our outcome variable, right? Insofar as our outcome variable is a random variable. So, broadly speaking, random variables get at the idea. Ooh, sorry. Okay. Random variables get at the idea of random outcomes, right? Outcomes that are not known with certainty. Right here, outcomes that are not known with certainty, right? Because there is randomness in the outcomes, right? There are some uncertainty, there are some randomness in the outcome. We can use probability to describe the possibility of each outcome. We can use, let me repeat this one again, we can use probability to describe the possibility of each outcome out of all the possible outcomes. And last week, we touched on the idea, this basic idea of random variables, right? Discrete or continuous, right? Discrete, such as coin toss, sex at birth, right? You can map all the outcomes, right? And you can assign numerical values to all the outcomes. Continuous random variables, on the other hand, are continuous, and the value are slightly more difficult, right, to quantify. If you think of GPA, right, you have a lot more options than sex at birth, gender, or coin toss. Right? You can have a wide range of GPA ranging from 0 to 4, right? You can have 3.832, 3.833, and things like that, right? You can have a lot more options, so to speak, when we talk about continuous random variable. Okay. And I raised this point last week, right? And I want to rehash it again. So why is probability distribution useful? Why do we need a probability distribution, right? Maybe this is the first time you've heard someone talk about probability distribution, and you might wonder, and you can justifiably ask, why do we have to talk about this? Why can't we just, put data into SPSS and run something, right? Again, having some basic understanding will help you go a long way, because if you understand probability, even you don't have to be able to calculate, you don't have to be able to do things with probability, but if we have some basic understanding of probability, things will make sense when we talk about significant testing. What is the p-value? What does it represent? What does it signify? Things like that. Okay. So again, probability distribution for random variables is useful because the most important thing is it has certain properties that we can work with, right? And let me give you a more concrete example. Let's say this is the data we have from time-in. Okay, let's say that we know a little bit about the height of time-in, and it is somewhere between 150 to 190 centimeters. This is the actual data point from 1990s. I think things will change by now. Things should change by now. But this one comes from the 90s. So if we know that time-in are between 150 to and 190 centimeters. And we also know that Thai-men are about 100 centimeter, 170 centimeters tall, right? If this is all we know about time, this information is almost useless. We can't do anything with it. We have these three numbers, and that's it. We can make sense of these numbers. We can relate these numbers to other things we know. Right? Basically, we can't learn much from knowing just these three numbers. But if we know that the height of Thai-men is normally distributed, the height follows a normal distribution. If we know this fact, we can actually go beyond these three data points, and we can do things much more than just reciting 150, 170, 190. Right? What else can we do if we know that the height is normally distributed, or we can say the height follows a normal distribution? Right? So a normal distribution is one of the many probability distributions. It just so happens that this one is very, very common in the natural world. You see probability distribution follow. A lot of natural phenomenon follow a normal distribution. So that's why you hear people talk about normal distribution. You see examples of normal distribution. And in almost every statistics, I think in every statistics textbook, you see this distribution being presented, usually the first one. But just so you know, this is one a normal distribution is one of the most common distributions. It is not the only one. Later on in the class, we'll see another distribution from the same family, and it is called a T distribution, right? A T distribution. We'll see that later on. Now, let me remove this one so you won't get confused. This normal distribution has this bell-shaped curve, right? It looks like a bell shape. And we see this, like I said, everywhere in the natural world. I told you earlier, there are some useful properties of probability, right? And one important thing, one important quality about the probability is that one important quality of the probability and probability distribution is that the area under this probability must sum to 1. So the area under the curve must be equal to 1, right? And we write it as, we write it like this. So, you know, regardless of the points we have, regardless of the numbers we have on the x-axis, when you sum the whole thing up, the probability must be equal to 1. So this is one important useful information we can use from probability theory to apply to statistics. Okay. Oh. For example, now that we know that probability must sum to 1, we can find out right here, right? We can figure out how much what's the area in this shaded region? How much is the area in this region, right? You can sort of find ways to calculate that, and I have done that for you. And this one takes about 95%, right? You can figure out an area under the curve, and this is about 95%. So this means this region accounts for 0.95 right? Out of 1. So again, the point is not to get you to calculate things under the curve, right? The point is, if we know a little bit about probability, we can conceptually think, well, probability must sum to 1. That means all things under this curve must be equal to 1. So we can partition areas, right? We can partition areas under the curve, and we can ask how much percentage is in that region, things like that. Okay, so that's one useful thing that we can get from probability. Okay, I hope this will wake you up. I hope this. ครับ
สวัสดีค่ะ just greeting sorry for being late
โอเคครับ
สวัสดีครับ
Class is okay right
Yes yes
yeah this is afternoon you know class and then after lunch I understand okay ค่ะ continue ค่ะ just come to say hi
โอเคครับ ขอบคุณครับ All right, so a good pause between probability and statistical inference, right? Again, let me rehash this point. I told you last week, statistical inference is about underlying probability distribution of data, blah, 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 right? And I, threw you big words last week, right? I gave you one example, but this time I have a better example to illustrate what we mean when we talk about statistical inference. All right, so there are a couple of steps we take when we conduct statistical inference. Let me walk you through a few. Statistical inference starts with this basic idea. And that basic idea is that we have observations in our hand. The only thing we have in our hands is data points, observations. This is what we have, right? Imagine imagine going out collecting data and have a grab bag of data. This is all we have in our hand, right? We can denote observation. Let's say we can denote it as Y, a big Y. This is a horrible handwriting. Let me try again. Right? We can say, Y refers to observations, right? And you may see smaller Y, right? Y1, Y2, Y3. These are all, observation number 1, observation number 2, observation number 3. Right? Okay. This is just notation. There's nothing to worry about this. But what we have again is observations. We start with this basic notion. And now that we have observations, another step is we think to ourselves, well, these observations must come from somewhere, right? These observations must come from somewhere. So there must be something. There must be something that generates the observations we happen to have in our hand. We think that the observations we have come from somewhere, and we think that somewhere is a machine. And this machine splits out the observations. Imagine, suppose there's a machine flying above us. Imagine there's a machine hovering above us, and it spits out data, right? And the observations we have, they pattern according to some data generating process, right? The observations we have, the data we have, pattern according to some data generating process. And the observation that we happen to have, these observations are just a subset of all the possible things that this process splits out. So our goal in statistical inference is to use, let me scroll down. Our goal in statistical inference is to reverse engineer the process. We want to use the observations we have to figure out the settings, right? We want to figure out the settings of this process from the observations we have. That's, in plain English, the goal of statistical inference. To use observations, to use data we have to figure out the settings of the data generating process. Now, this is in the afternoon, and I think everyone needs a cup of coffee. So I have analogy to help you understand all of this. Okay, and I call this a coffee maker analogy. I'm sure everyone loves coffee. Suppose your friend, you walk into a room with this coffee maker, and suppose your friend makes you 3 cups of coffee. This is number 1, right? This is the first cup, the second cup, and the third cup. Let's say your friend makes you 3 cups of coffee from this coffee machine, and you taste the 3 of them, and you say you love this third cup. This is the best cup. And you absolutely hate the first cup, right? You are okay with the second cup. The second cup is okay. And your friend tells you, well, I use this coffee machine, right? And these 3 cups come from this coffee machine. So if you want to find out how this third cup was made, what would you do? You wouldn't ask your friends to make you 200 cups and, taste all of them, right? You would instead ask your friend, hey, which buttons did you press, right? You would probably say, hey, which button did you press? How did you come out? How did this third cup come out? Which button did you press, right? So you want to figure out the settings, right? This is an analogy here. You want to figure out the settings that give you this third cup of coffee. And statistical inference is exactly like making a cup of coffee. You have these cups of coffee that your friend makes you, right? And you want to try to figure out which settings give you, the third cup, the first cup, or the third, or the second cup. So I hope this is clear. I call this a coffee maker analogy. Okay. And before we move on, you can use this handout, the PDF that I have, in any way you like, but please do not share this PDF with your friends who are not part of the program, because I haven't had the copyright stuff. I basically copy and paste images from the internet. So please do not share this one just yet. I haven't had the right kind of copyright statement in the PowerPoint. I don't want to go to jail because, I happen to break a copyright law. Okay, the coffee machine analogy for statistical inference. All right. Now, with this analogy in place, we can go back to the text and replace some words with an appropriate set of terminology. Right? I'm gonna go back to the same thing and replace some words with the correct terminology. Observations. Right? Observations are your outcome variable. Scores, reaction times, English proficiency test scores, motivational profile of your students, you name it. Observations are your outcome variable, right? The observations, the things you observe for your outcome variable. A data generating process, we can replace this word with a probability distribution. And probability distributions have settings or parameters, right? I'll get back to this in the next slide. But for now, just so you know, data generating process is a probability distribution. And probability distributions have settings. So to figure out the setting is to find out the parameter values of that particular probability distribution. So this whole process of statistical inference is just this, using observations, your outcome variable, to figure out parameter values that govern a probability distribution. Some big words, we can't avoid that. Just so you know, there are some big words there. But if you take time and digest it again, you will see, go back to the coffee maker analogy. It will get at the heart of statistical inference. So hopefully so far so good. Okay, now I told you I'm gonna talk about this a little bit, right? Probability distributions have settings, and these settings or parameters dictate the look of the distribution. What do these sentences actually mean, right? Let's go back to our running example. Let's go back to the normal distribution. Again, just so you know, this is one of the many distributions you see, right? It just so happens that this one appears again and again in the natural world. Right? So it's easy to talk about because we know things about the average, the mean, or some standard deviation. Right? The normal distribution. A very quick note, you may see the word Gaussian distribution. A normal distribution or a Gaussian distribution are pretty much the same. Gaussian, the word Gaussian comes from a German mathematician, Carl Friedrich Gauss. I think I pronounced his name right. If you stumble upon a statistics textbook and you open it and you find the word Gaussian distribution, don't be confused. They are the same. A lot of statistics textbooks will say Gaussian distribution, or sometimes in the same sentence, people might say a normal distribution and then a Gaussian distribution, right? Just to have some variability, just so you know. So in a normal distribution, there are two parameters. The first one is the mean, and the second one is standard deviation. I threw out these two things last week, right? I never explained what they were. Now, I'm gonna do that. Now, if I said, well, I think scores are generated from a normal distribution. This is, if you can't remember this is okay, all right? This is just a notation. This is a scientific notation. When we say scores come from a normal distribution, scores are normally distributed. This is how you can write a notation for that. Scores, this symbol means is distributed as or follows. So we say scores follow a normal distribution. And in parentheses, we have to say the parameters of that distribution. And there are two here, right? So the first one is the mean. And the mean or the average is a location parameter. It tells us where the center is. It tells us where the center point of the distribution is. The second parameter is called standard deviation. And this is called a scale parameter. Again, if you have trouble understanding location scale, that's okay. The gist of the standard deviation is it tells us how spread out the distribution is. I'll show you a few examples in a minute. Sometimes you may see this thing. Oh, pardon my handwriting. Sometimes you may see this thing, and this is variance, right? This is standard deviation square. You raise it to the power of 2, right? They are pretty much the same in this context, all right? Sometimes you see some people use variance, just so you know. It's pretty much the same thing, similar to standard deviation. All right. So we talked about normal distribution, and we know when we talk about normal distribution, we need 2 parameters: the mean and the standard deviation. And what information do we have from knowing the mean and the standard deviation? Right. The first one on the left here, this one right here, right? The larger the spread, the larger the standard deviation, the fatter the distribution, right? So standard deviation, as you saw in the previous slide, the standard deviation tells us how spread out the distribution is. This one, the one in blue, has a bigger standard deviation, and we call it a fatter distribution. So it's much more spread out. The one in red, this one has smaller standard deviation, right? So it's much more truncated. Okay, so this standard deviation tells us how spread out the distribution is. In contrast, when we shift the mean, when we change the mean, when the mean changes, the distribution, the center of the distribution changes. The one in red, this is when standard deviation is, when the center, the mean is at 40. This is when the center is at 60. So again, the mean, the center, right, where the center lies. The standard deviation, in contrast, how spread out is the distribution. Okay. I want to, go through this a little bit slower. I don't want to rush you through this because it takes a little bit of mental gymnastics, right, to figure out what these 2 terms mean. All right. If I go too slow, just raise hand, tell me faster, right? Okay. Now, this is the part where you see some symbols. If you can't remember them, don't worry. The idea I want to get across is in the kind of analysis we often use, in the kind of analysis we often do, when we try to figure out parameter values, it turns out we can use the information we have. This is the gist. We can use the information we have in our sample to estimate parameter values. And instead of going through some heavy mathematical calculation, we can just use what we have in our data. And we can use the average, the mean that we calculate from our data, and the standard deviation that we calculate from our data to stand in for the parameters, right? So we can use the mean, the average, X bar here, to stand in for the mu. And we can use the standard deviation, again, that we can calculate from our sample to stand in for the sigma, for the standard deviation in the population. Okay, and if you, just a quick recap, this means if your data set consists of, say, 4, 5, 6, 7, 8, 9, right? Let's say this is all you have. This means you add them all up, right? And divide by the number. So we have how many? We have 1, 2, 3, 4, 5, and 6. So we divide by that. Get the mean, the average, the center, right? And the standard deviation, again, is this, how spread out is the distribution. If you notice, when we talk about how spread out, to be more precise, how spread out from the center, right? Because we use each one, right? We subtract each one, right, with the mean. So the basic idea of the standard deviation is how spread out from the center, right? Okay, I'm not going to go into any more detail, but just so you know, we don't have to go through in frequentist analysis. We don't have to go through some kind of mental gymnastic. We can use the samples we have to figure out parameter values, to figure out the setting. Okay, by using the mean and the standard deviation we calculate from our sample. Any question or any concern, any issue? Parameter values are variables, right, Ajahn? They are variables. Let me go up. They are variables, or we think of them as variables at the population level, right? Oh, sorry. We think of them, right? The mu, the standard deviation here. We think of them as variable at the population level. But what we have is this one, right? Did I answer your question? If you have any questions, feel free to type them up, right? I'll try and answer them as we go along. Okay. Let me scroll this down a bit. Okay. All right. So this is statistical inference, right? With a little bit of math here and there. Now, last week, this is where we left off, right? I talked a little bit about sampling distribution, and I think I didn't do a good job. And I'm pretty sure I must have confused you or some of you. Now, let me go back to this idea again and clarify what I meant. Right? But before that, there's one thing I wanted to tell you. So far, ooh. Okay, so far, let me try and get this part done. There's another question. Okay, I'll address that in a few minutes. But let me get this idea across first. So far, I've told you things about statistical inference. So we have to use the data to figure out this and that. We need the samples, and we can use the samples to go look at the population values and things like that, right? So far, all the things I've said, it's as if I was preaching the gospel. It is as if everything was the truth, right? In reality, the situation is much more complex. One thing you've never been taught in statistics class is that statistics is full of assumptions. Statistics has a lot of assumptions. When we say, for example, the data the observations that we have come from some process, right? That's one of the assumptions. In reality, we may not even know what that process is, right? So far I've told you, oh, scores come from a normal distribution. You might deep down, you might think, how do I know? And to tell you the truth, sometimes it may be true, sometimes it may not, right? So this whole idea of data generating process is in fact one of the assumptions. We may not even know what the process, the actual process looks like. We may not even know if it's like truly normal and things like that, right? But all we know, and this is the thing that frequentist analysis is very good at. All we know is the data, things we have in our hand, right? We have the sample with us. So if we can use our sample, to construct some distribution such so that we can use that distribution for our analysis, wouldn't it be better? Wouldn't it be easier? And the answer is probably yes, right? And this is sampling distribution. This is the whole idea of sampling distribution. We may not know what the actual distribution is, but since we have data, since we have sample, we can do something with it, right? So why don't we use sample, the things we have in our hand, to construct some kind of distribution? And we can use this hypothetical distribution to test statistics, to test some significant levels and whatnot. So this is the story behind sampling distribution. And last week, I showed you an example of some experiment, right? I thought it wasn't too clear. So let me try again. Suppose, again, let's stick to the running example, right? The height of Thai male population, right? Suppose we randomly select 40 Thai men and we measure each person's height, right? And then we record the height and we plot a distribution of these numbers. Let's say, this graph represents 40 randomly selected Thai men. And this is the distribution we have. This distribution represents the sample we are able to obtain. If you must know, this one is called a sample distribution. Again, you don't need to remember all these terms, but I'm just throwing them out there. Again, a sample distribution represents the sample, right? The things we have in our hand, and we plot them. We see the curve, the shape of this distribution. Okay, so imagine further. Let's go big. If we can repeat this whole process 1,000 times, and each time we record the average height of the 40 men we select, and we plot the averages or the mean, right? And after we plot all those averages, we also calculate the grand mean, the grand average, and the standard deviation. What we get out of this when we select 40 Thai men, we record the height, we calculate the mean of those 40 people, we select another group, we do the same thing again and again 1,000 times. The idea is that, even if what you have may not look like a normal distribution, what you have right? The sample you have, it may not look like a normal distribution, but if, in theory, if you repeat this whole thing again and again, if you repeat this whole process again and again, and you construct a sampling distribution, if you construct a sampling distribution, you eventually get to something that looks very normal. You eventually get to something that looks like a normal distribution. And so this is an example of a sampling distribution of the mean. And we are going to use this sampling distribution in significant testing, right? Again, the basic idea is we may not know what the actual distribution looks like, but if we repeat this thought process, if we work with the sample we have, and if we plot this hypothetical process, we will get to something that looks normal. This is just so you know. From this distribution, we can calculate the standard deviation, right, of this sampling distribution. And for this example, I have about 1 right here. So if you round them up, this is about 1. Okay. Just ignore the code above, right? But the basic idea is you can also calculate the standard deviation of this distribution. And in this example, we get something that is almost equal to 1. Okay. An interesting fact, one interesting fact is that you don't have to do this in real life. You don't have to resample from your sample. You don't have to go do this by hand. You don't have to construct this distribution by hand. You can infer, you can come up with this sampling distribution from the sample you have. And a good way to prove that is to do something which is to calculate the standard error of the mean, which is the standard deviation, all right? If you don't know what this is, just think of it as a standard deviation. The main point I want to get across here is to show you, again, that we can work from our sample. We can use our sample to construct, to build a sampling distribution. And if you calculate this, you'll get something that's about 1. So this is a quick proof that they are exactly the same thing. Okay, now let me, there are answers. Okay. Okay. So there are 2 answers. So let me try and go back and address them. All right. Ooh. Now, the 2 questions. Okay. The variance, right? Okay. Quick answer, variance and standard deviation. They get at the same thing, right? Variance and standard deviation get at the same thing. The idea of how spread out, right? The easiest answer in terms of the difference is that if you let's just take this part, right? I'm not going to go into detail in terms of the formula, okay? But the basic idea is if you subtract one value, let's say the mean is 7, right? Let's say the mean is 7, and you subtract 6 out of 7, right? You'll get minus 1. If you subtract 8 out of 7, you'll get plus 1. Okay? If you go through this whole thing and you sum them up, you'll get to 0, because negative values will cancel out positive values, right? And you'll get 0. So in the calculation of variance, at a certain point, you will try to remove all the signs, negative, positive. You will try to strip them out, because you don't want to get to 0, right? You don't want to get to 0, because if you happen to get 0, it means there is the distribution is not spread out. There is no variability. And that is not true. Everything contains variability. Things are near or far the center of everything, right? So the basic idea of the variance is, let's try to cancel this. Let's try to cancel these symbols, negative, positive, right? And get at the value. So that's the variance. It contains the same kind of information as standard deviation. It just, again, it takes away this symbols, the sign, positive, negative. Okay. Another question. Again, I'm not gonna try and go into detail. This idea, why do we have to have minus 1 here? Why can't we just use n, right? The answer is, in some instances, you will see just an n. For some other instances, you will see this one. The basic idea is, if you minus this, if you have minus n, right? You try to estimate, you try to get at the population. Let me give you this basic answer, right? The actual answer, now let me tell you this, the actual answer involves degree of freedom. And that will take about half an hour to 45 minutes to explain. And it's one of the most confusing things. All right. So just so you know, sometimes you will see an SD with an N. Sometimes you will see it with an N minus 1. With a lot of sample size, with 50, 60 participants in your experiment, this doesn't really matter. You have the same answer, right? But the formula here is just to let you know, well, we're trying to estimate a population parameter, things like that. Does that answer your question? Is that okay? Is that okay, ครับ ดวงกมล? Hopefully they are, right? But again, the actual answer will have to deal with degree of freedom. Okay, and I try not to get into that. Now, okay, let me scroll down to where we were. All right, okay. Sampling distribution. Let me repeat this again. It is the main component of statistical inference. We use the sample we have in our hands to construct this hypothetical sampling distribution. And this distribution is something we can use to test our hypothesis. Okay, this is why, we need to talk about sampling distribution, even if it, at first glance, it doesn't make sense, right? Why do we have to sample from our sample again? What's the purpose of that? The idea, again, if you take a stats class, you'll be presented with a sampling distribution. You might ask, what is that? Why do I need to learn about something that's super hypothetical, right? Something that doesn't even exist in the real world. The idea is, we may not know what the actual distribution is, but since we have our sample, we can use our sample to our advantage, right? We can use our sample to our advantage, and we are going to use our sample to construct sampling distribution. And this sampling distribution nicely leads us into significant testing. Okay. Now, a little bit of story. Now, I think this is about time to stop talking about, some mathy stuff and to tell you a little bit about story instead. Significant testing, as we know it, is actually a very recent innovation. Statistics, the kind of things we do, model comparison, inferential statistics, or, t-test, ANOVA, and things like that, they are relatively new. This whole enterprise of statistics, the things that we are talking right now, the things that you study in class, it was developed in the 1940s, 1930s. Roger Fisher and Jerzy Neyman started this whole enterprise. It came into being just in the 40s. Think about this. This is just what, 80 years. How could 80 years of something cause us so much pain, right? But it is. It is actually a relatively new thing. But we often study statistics as if it's, like I said, it's a gospel. It's like the teachings of the Buddha or the teachings of Jesus. It is not. It involves a lot of assumptions. There's a lot of stories behind statistical analysis or significant testing. I can give you the name of the book if you are interested. It's just 100 something pages. It's written by a student of Jerzy Neyman, and he recounts the experience, from these two camps, Ronald Fisher and Jerzy Neyman. They, a little bit of story here, they started out working on the same thing. They were interested in this idea of comparison that led to significant testing. They started out from the same angle, right? They approached it from they worked through the problem and landed on two different kinds of testing. And towards the end of their life, they hated each other. They trashed each other in journals, in conferences. Roger Fisher said, Jerzy Neyman's approach is stupid. I don't understand why you need to do this and that. And Jerzy Neyman came back and he said, Fisher's idea is foolish and things like that. It was super acrimonious. They hated each other so much, right? But one funny thing about them and the two approaches they sort of championed, they didn't see the two approaches being compatible. But in statistics class that we do nowadays, the statistics class that you may happen to teach, the statistics class that we the materials we studied in statistics, these two ideas come together. Sometimes you see, or you may hear people say, oh, you use p-value to reject an alternative, you use p-value to reject the null hypothesis, and then you accept an alternative hypothesis and things like that. The story behind this is Fisher came up with p-value, and p-value is only for the null hypothesis. Jerzy Neyman came up with alpha and beta null hypothesis and alternative hypothesis, and he doesn't see the role of p-value in accepting or rejecting the null or alternative hypothesis and whatnot. So a little bit of history there. The two views are not compatible, but right now when we study stats, they are somehow combined together as if there's like a single unifying approach to significant testing. The answer is no, there is no single approach. Okay. And I think if you're interested, that book is worth reading, because you see the reason there's a lot of confusion with p-value has to do with us combining approaches, blending things when they were not meant to be blended. Right? Okay, a little bit of story there. But for our session today, I'm not trying to litigate the two approaches. I have to tell you the truth. This is, in all honesty, I've never understood type 1 and type 2 error. If you've never taken stats before, type 1 and type 2 error are things that are associated with the word alpha and the word beta. It has to do with the power of a statistical analysis and things like that. To tell you the truth, I've never understood type 1 and type 2 error. Even like 10 years of trying to understand this, trying to study this. So if you are starting out, and if you have trouble understanding stats, you are not alone. Okay. In our class today, we are going to focus on significant testing. We're going to focus on the idea, the concept behind p-value. I feel that this is much easier to explain, and it's much easier to, with misconceptions stemming from p-value, it's much easier to correct. I am going to leave type 1, type 2 error to other experts. I will not be able to tell you what they are. In fact, like I said, I have trouble wrapping my head around the two concepts. But we will talk about p-value, and I'll try and do my best to explain, to tell you what p-value is and where the breakdown happens, why people get confused with p-value. And p-value in Ronald Fisher or Fisherian's approach, p-value is under this thing which is called null hypothesis, significant testing. Okay. The gist of significant testing is we want to compare models. We want to compare two things, right? If you have trouble understanding what models are, right? Let's just take the word models out, right? Let's say the goal is to compare two situations. Okay, let's strip away the word models, use the word situations instead. The goal in null hypothesis significant testing is to compare two situations. If we'll call the first situation a zero situation, right? We'll just say the first one is a zero situation. Broadly speaking, a zero situation is the one where nothing happens. There is no effect, or the effect is zero. This is a zero situation. We want to compare this zero situation with the other one. The other one, let's just say our situation. Right? This is one where we have data. Right? This is the situation that we have, the observations that we have. We want to compare our situation to the zero situation. And specifically, we ask if our situation could be part of this situation. Our situation, is it part of a zero situation? Right? Now, if you understand this, take the word situation out, replace it with model, right? This is the idea behind null hypothesis significant testing. We want to compare what we have right here against this here, the null, the zero situation. So what is a zero situation? What is this thing, right? So the correct terminology for zero situation is the null hypothesis, right? Let me replace that with the right term. And when we say, oh, the null hypothesis, what do we mean, right? We construct this hypothesis with some fixed value. We give it some fixed value. And this value can be anything. This value can be anything. But it usually happens to be zero simply because, you know, in the kind of research we do, in the kind of experiment we do, right? We want to test some learning, or we want to observe some improvement. We want to see the effect, right? Some learning. We want to see some improvement. So this, more often than not, the null hypothesis often has zero as a fixed value in the kind of research we do, right? If you think back to the example I showed you last week, and I'm going to present that one to you again. You have training, right? And you want to see if the experimental group improves, and you want to compare that improvement to the control group, the group that doesn't receive any kind of training. So in that kind of situation, when you compare two groups, you have experimental group and control group. And you say, how much does group X improve, right? You think of improvement as either zero, which means no improvement, no learning. Nothing gets better, right? You compare that to something that is perhaps positive, right? So the idea, again, is null hypothesis having some value, okay? When we say we fix the value at zero, right? When we say the null hypothesis mu equals zero, when we fix the value at zero, what does this actually mean? Right? Usually when we talk about null hypothesis, you just say, oh, mu equals zero, and that's it, right? What does it actually mean behind the scene? Well, it means we set up a probability distribution for our zero situation. We say the effect, let me repeat, we say the effect is zero or there is no effect, right? What we actually mean is that the distribution is centered around zero. So the null hypothesis becomes some kind of probability distribution. And this is why I keep hammering home the idea of probability. This is why I said, you know, earlier, oh, you should try and wrap your head around probability, because it's actually meaningful. Okay, let me repeat again, the null hypothesis, when we say, oh, mu equals zero, there is no effect, there is no learning. What we actually mean is that we are going to construct some kind of probability distribution. And that distribution will have the center at zero. And this is a visual representation. I'll go back to the previous slide, but I want to show you this one first. When we say, oh, our null hypothesis equals zero, what we actually mean, again, is that we are building. We don't do it ourselves, right? We ask the computer program to do it for us, and the computer program has things like a lookup table and things like that. They don't really actually build a distribution, right? But in theory, this is what we do when we are setting things up for null hypothesis significant testing. Okay, so this one right here, just to show you that it is centered around 0. Okay. So this is our null hypothesis. Now, from this is the first thing we do. Now that we have this whole idea set up, right? The next thing we do in significant testing, we ask how far our sample mean falls from that center, right? We ask how far our sample mean falls from that center. So let me scroll it down a little bit here so you can see. We ask, say, let's say this is our sample right here, right? We ask how far is it from the center, from the mu of 0? How far is it, right? If it is not far, if it is near the center, if it is near this straight line, we say that perhaps this point, our sample mean, is consistent, is likely to be consistent with the null hypothesis. This takes some time, right, to get used to. Let me repeat again. We have constructed a null hypothesis distribution, right? And we say, well, because the effect is 0, this distribution is going to be centered around 0 right here in this graph, in this figure. And we have our sample, we have data. Let's say we have the mean, the average. We ask ourselves, is this point far or near this point, right? And if it is near, if our sample mean is near the center, the mu, we say our data are likely to be consistent with the null hypothesis. I'll expand on this in a few minutes. Again, if it's near, we think our data are likely to be consistent with the null hypothesis. If, on the other hand, if our sample mean is far from the mu, we say, well, it's probably not consistent with the null hypothesis. I'm going to come back and try to define consistent or not consistent. And this is where the breakdown happens when people misinterpret, when people perceive p-value to be something else, okay? So how do we go about establishing the distance, right? How do we go about measuring the distance? How do we know if it's far or if it's near? So we measure this distance, the one right here, right? Let me repeat, this is our sample mean. We measure this distance with something called t statistics or t value, right? We use something that's called t statistics. What we get is the t value. what it does, again, is to capture this distance right here. I want to pause here for just about a minute or two and ask if everyone is still okay with this idea. Is everyone still okay? Okay, okay. Good, good, good. Okay. I'll take that as a word of encouragement to go deeper. All right, so we construct this model. That's the first step, right? The null model, the null hypothesis distribution. And then we measure the distance. We measure the distance. We use what is called a t-statistics. We measure it and we get t-value. Okay? The next step, that again happens behind the scene. SPSS or MATLAB or whatever program you use, they all do it for us, right? After we get the t-value, what we do next is we check the probability of that t-value in a t-distribution. So like I said earlier, a t-distribution belongs to the same family as a normal distribution. This is not the most scientific thing, but I'm going to draw you examples of a t-distribution. But just so you know, this is this is not the most scientific way to do that. Let's say our normal distribution. Okay, looks good. The t-distribution is, oh, let me change because you won't be able to see that. Let's see. Okay, this is way better. Let's say this is our normal distribution. Like I said, t belongs to the same family. The only difference, visually speaking, the only difference between the t distribution and the normal distribution is the tail end of the probability. Let me change the color here. A t distribution would look something like this. Like I said, this is not, again, this is not the most scientific way, but just want to show you that the one big difference between the t value and, oh, sorry, the t distribution and the normal distribution lies at the tail end of the probability, the tail end, right? The end of the probability on each side. So t is, if you hear a background noise, I'm sorry about that. There's like a truck driving past by trying to sell things. But anyway, the t distribution, right? The t distribution assigns higher probability in this area, in the tail area. The normal distribution tapers off quicker. If you look up on the Wikipedia or some statistic textbooks, you will see that scientifically they would say a normal distribution tapers off more quickly, but the basic idea is this, right? Sorry, there's much more probability in the tail ends of the t distribution. Okay, let me step back. We get the t value, right? We get the t value. We check the probability of that t value in a t distribution. So this is the process. It looks something like this. This is a t distribution. If if let's say we get a t-value of, let's say 2.5, I'm making stuff up, okay? We asked, what's the probability of this t-value in a t-distribution given the null hypothesis? So 2.5 is somewhere around here, right? Let's say 2.5 is here. And so we check the probability. We check the probability. What's the probability of this side of the distribution, right? And we may find out that the probability is, say, making stuff up. What we actually do is, we are asking how much area under the curve, right? We try to figure out how much area under the curve in this region of the graph, this region of the distribution, right? So if, after we check the probability, if the probability of that is less than 0.05 or p less than 0.05, what we do next is we reject the null. If you find that this process is super convoluted, just know that it is. Again, we set up the null distribution, right? We check where our sample mean falls with the t-value. Now that we have the t-value, we construct a t-distribution, and we ask what's the probability of that t-value, right? If the probability is less than 0.05, we think our data is not probably consistent with the null hypothesis. I'm emphasizing each word here because this is where I said, again, misinterpretation happens. When we reject the null, what we actually do is we say, we think our data, we think our sample mean is not consistent with the null hypothesis. Sometimes you may hear people say the p-value is the probability value of a statistic given the null hypothesis, and that is also true, right? You may see this probability in a statistic textbook. It's called a conditional probability. The probability of the statistics when the null hypothesis is true, when we assume that the null hypothesis is true. If we get this value, right, if it's lower than 0.05, what we mean is that our sample is not consistent with the null. Our sample, in layman's term, you can say our sample does not seem to come from the null hypothesis. This, after all these steps you have taken, this is the only thing we can say about p-value. We reject the null. And what we mean by that is that we don't think our sample, our data, are consistent with the null hypothesis. Okay, a lot of big words, a lot of me, screaming into your face. This is what p-value is. This is what it means, right? And I walk you through the whole process. Not the whole process, but some ideas. with a little bit of visuals here and there. Now, I like to take the next 10 to 15 minutes. We will not, I'm not going to give you 10 to 15 minutes. I like to give you about 5 to 7 minutes to look through this, and then we'll discuss each of these statements. Given what you know about null hypothesis significant testing, given what you know about p-value and things like that, I have these 5 statements, and I want to ask you to think through each one carefully. Is it true or false for each of these statements? Is it true or false? I'm going to give you about 5 to 7 minutes, right? And then we'll talk about these 5 statements together. I hope everyone is still doing okay. Don't fall asleep just yet. Okay, about five more minutes. Think deeply about each statement. Is it true or false? Categorical answer here. There is, just so you know, there is no half true, half false. The answer is categorical. It's binary here, either true or false. Okay. 2 to 5, true, but not sure about one ajan. Okay, I think all of them are true, all T's. Okay, now, for some of you who are afraid to answer, we have a raise hand button. Okay, so let me go through each of the statements one by one. And number one, who thinks it's true? Can you please click raise hand? Raise hand if you think it's true for number one. Okay. Anyone else? Anyone else? Can you please raise hand if you think number one is true? You can see a button on, if you click chat, I think if you click on chat, you will see a button and you will see the word raise hand. Okay, let me note down. Okay, we have one respondent here. Number two, who thinks it's true? Can you please raise hand? Raise your hand, please. 1, 2, 3. 3. 3. Okay. Number 3. Raise hand, please. Raise your hand if you think number 3 is true. 1, 2, 3. 4. 1, 2, 3, 4. Okay, let's say 4. Number, I'm using the laptop. I don't know where it is. Okay, I don't have that sticker. That's okay. You can type up your answer. You can say, I think it's true. That's okay. I'm just coming up with some rough estimate. Okay, that's okay. Number 4, how about number 4? I put all trues. Okay, number 4. If you can raise hand, just show your hand, please. About 3, 4. Okay, true. 3, 4, 5, 6. Okay, I'll say 6. The last one, number 5. If you can raise hand, please do. If you can't, just type true or false. Okay, 1, 2, 3, 4, 5. Okay, 5. 5. Okay. Okay. 1, 2, 3, 4, 5. And we have 1, 3, 4, 6, and 5. Okay. Hands down, please. Here's the answer. Okay. Would you be surprised if I tell you they are all false? They are all false. These are all wrong. Yes, they are all wrong. And I'll walk you through the concept and I'll tell you why it's wrong. They are all wrong, but these are the things we hear all the time. These are the things we make all the time when it comes to p-value. They are all wrong. Okay. And it is mind-boggling, yes. It is interesting, just so you know. As an aside, if from now on, I'll tell you why they are all wrong. Okay, and it boils down to this basic idea of the word rejection and significant and things like that. They do not mean what we think they mean, or they do not mean what we think when we use them in our daily life, significant and reject means something completely different from the ones that we see in this context. But as an aside, if and this is one of the things you can still hear from professionals in the field. If someone tells you, let's say someone asks you about your research, and you tell them, oh, I do this, and I do that, and I find this and this and this and that. And if that person says, yeah, it's interesting, what's the p-value? What's the p-value and things like that? Is it significant, right? And then you said, oh yeah, this part of result is significant, and I got a p-value of, let's say I got a p-value of let's say, oh, and for this part of my research, I found a significant effect, and I got a p-value of 0.04. Okay, and that person says, well, you got a p-value of 0.04. I think you'll have a hard time trying to get your work published. That p-value is it's too high. You need to go down to, let's say you need to go down to 0.001. If you get into this kind of conversation, and if someone tells you, you need to get a p-value of like 0.001, your 0.04 is too low, it's too high, smile. Just tell that person, oh, interesting, yeah, and then get out of that conversation. Because it's all wrong. Now, let me start with this idea. When we talk about p-value, and we say, well, if the p is lower than 0.05, we are going to reject the null. If it's above 0.05, we will not reject the null. Okay, you can't even say, now this is true, you can't even say you will accept the null. There is no such thing as accepting the null hypothesis. Let me go back to this one again. Let me hammer this point home. What we say, right, from this distribution, right? Say we measure the p-value, we ask, we start off from the null hypothesis, right? We ask if our sample, the data we have, let's just say data, if our data are part of the null, that is the only thing we can answer. If the p-value is low, and this p-value is when the null hypothesis, when we assume that the null is kind of true, right? I'm going to use plain English here. The value that we get when we know that the null is sort of our working assumption. If it's lower than 0.05, the only thing we can say is we don't think that this value is consistent. We don't think that this value comes from the null. So we are going to reject the null. When we reject the null, we are not saying that the null hypothesis is wrong. We never know if it's true or false to begin with. That's not what we meant to, right? Let me scroll up again. In this distribution, there is no such thing as correct or incorrect in this distribution, right? Plain English here, right? To begin with, the only thing we want to know is that, is this one, is this data point consistent with the null? Is this one part of this distribution? So if we start off with this, the only thing we can say is, yes, consistent. No, not consistent, right? This is the only answer we can get when we conduct significant testing. Our goal is not to say no is false, no is true. Our goal is simply, is my data part of that? Is my data part of the distribution? So you can say, yes, maybe part of it. No, maybe not, right? That is all you can say about the p-value. And the 0.05, sometimes you'll see the word rejection, rejection value, rejection point, or something like that. This is very arbitrary. Fisher proposed that maybe if this value, given the null, if we could observe this value, right, given the null, 5 out of 100 times, we think maybe this data point does not belong, is not part of the null hypothesis. So this is actually arbitrary. There's no reason why we, like I said, Fisher was equivocating. He wasn't really, he wasn't really into like 0.05. He said this is probably the right kind of yardstick, the right yardstick we could use. You can actually move this goalpost up and down, but it just so happened that the scientific community lands on this value. Okay? If you get a p-value of 0.0001, which means 1 out of 1,000 times, the answer will still be the same. You are not asking if, because again, we set out to find out if it's part of the null. We are not asking if it's very, very good evidence of the null, right? That's not what we want to test. So irrespective of the p-value, as soon as you land on something lower than 0.05, you say you reject the null. If you land on something that's greater than 0.05, you say you cannot reject the null. I hope this will not come as a surprise to you. So all of these, now let me try and go through each point one by one. All of these is all false. P-value is not evidence for any kind of hypothesis. Sometimes you will see the word compatibility, right? And that's all we can learn with p-value. Is it compatible with the null? Right? It does not mean, again, why is it not being true 1% of the time? Because that's not what we set out to test. We set out to test if our value belongs to that null, right? Okay, number one. So when you reject the null, number two and number three, when you reject the null, when you say, well, p is less than 0.05, I'm going to reject the null. It does not mean that the null hypothesis is wrong. In reality, we will never know if the null hypothesis is wrong or not wrong. The p-value is just a small part. If you think of model comparison, broadly speaking, think about this. If you want to compare, say, if you want to compare Toyota with Mercedes, right? If you have two cars, you want to compare Toyota to Mercedes. If you want to compare for like, like for like, you'll probably have to take down the two cars and you'll have to inspect each element of the car one by one, right? You have to look at the engine, you have to look at the wheels, you have to look at, all sorts of things, right? And you say, well, I've compared everything and I can conclude that they are the same, they are not the same, things like that, right? In statistical sense, when we talk about compatibility, we compare the null hypothesis, the null distribution, with our situation, with our distribution, right? The distribution is actually large. We go back to this one again, right? The distribution is huge. We are only interested in a tiny part of the distribution. We can't really say when we reject the null, we are interested in whether the point lands in here or in here, right? We have no idea how this whole thing is about, right? So to speak. So when, again, let me repeat, when we reject the null, the only thing we can say is not consistent with the null hypothesis. We don't even know if the null hypothesis is true or false. That's not what we set out to test. Likewise, if you get a non-significant test result, it does not mean that the null hypothesis is true. These 5 points trip people up all the time, simply because they think the P, the probability, is about the hypothesis itself. The answer is no, it is not about the hypothesis. It's just the compatibility. We are interested in the compatibility between our data point, right? Between our sample and the null model. Okay, so far so good. So this, I try to spend some time, I try to massage, I try to give you the right message here, because this misunderstanding is pervasive. This misunderstanding is everywhere. And you will probably run into this misunderstanding, misconception at some point in your professional career or in your work career. And one thing we can do, of course, we can try and correct that, right? We can try and correct that. We can try and preach the right kind of message, right? But another important thing we must do is that, if we can, we need to point out this misconception. The actual story is actually larger than this, right? I'm not going to go into detail about, what p-value is, what it does, what it doesn't mean, things like that, right? But there are a lot of misconceptions. There are a lot of misconceptions here. I'll tell you a little bit about how you can report this. But later on in our lecture, the upshot is you can still report it as if nothing happened. I guess we'll talk about that. We'll talk about that later. But the point I want to get across is this: you will, at some point in your life, someone will tell you your p-value is not low enough. Your p-value is too high. If that person is someone you can help, if that person is someone you can demystify the p-value, please do. If that person happens to be someone who holds authority over your educational professional career, my honest answer is play along, but know that that interpretation is wrong. When you grow older, when you have more authority, understand the issue. Try your hard to understand the issue and be the voice of reason. Correct other people, right? So this is playing devil's advocate here, right? You have to, again, like I said, if you find someone, your friends, your peers, someone you can correct. If you find someone who is not willing to listen, if you find someone who is not willing to be corrected, and that person has some authority over you, the only thing you can do right now is to play along, but know that that interpretation is wrong, right? This is not part of statistics. Anyway, this is not part of statistics class, but this is negotiating misconception that is so pervasive, because again, p-value is mysterious for a lot of people, and people take p-value as evidence for certain hypothesis. It is not. And that's why I walk you through the probability thing, because I want to show you some rough idea of what it means when we get the p-value, what it actually represents. There is more to this story. If you are interested, study stats. If you think this is convoluted, this doesn't make sense, study it, move on to Bayesian. I'm trying to sell everyone a Bayesian statistics. I think it's a cool thing, but it requires a little bit more understanding of probability. I'm not at that point yet, but I can tell you I can run Bayesian stats and I can interpret the results and things like that. So again, not knowing everything, it doesn't mean that you have to know everything to be able to do stats, right? There are certain things you need to know, but know what you don't know and improve. I think this is a very important lesson for each and every one of us if we are serious about stats. And p-value is a big thing in psychology, in linguistics. Nowadays, people talk about p-value, and there's actually one journal. I think there's one journal in psychology that bans the use of p-value. So there are other kinds of things that people add to this to p-value, right? And I haven't talked about confidence interval. I haven't talked about effect size. Those are things that people do to complement the black and white interpretation of p-value. That's I am not going to touch on those two things, but just so you know, there are more things to learn about, right? When it comes to statistics in frequentist framework, classical frequentist framework. Okay, so far so good. Okay, now the last part of the class, and I have a little bit about, I have something to say about reporting the p-value and things like that. Not a lot, but a little bit as part of the last part of the class. And I like to end, again, like I said, when I started out, some high-level conceptual understanding of linear modeling. And I think I can point you to some references in the end, or I can send you an email later if you are interested in pursuing this idea further. But why am I telling you about some sort of modeling? You might ask, right? You might think, well, isn't this like too difficult for me? Why are you talking about right now, right? I don't even have like basics in stats. Right? Believe it or not, in everything we do, we build a statistical model, t-test, ANOVA, correlation, you know, the kind of tests, the names you hear in, or the tests you hear in statistics, they are all models. They are some kind of model, and they actually belong to the same kind of model, and that's a linear model. But when we talk about stats, unfortunately, we often partition statistical models or tests according to some research question, right? And then we end up studying t-test. We end up studying t-test in one unit, ANOVA in another, and then correlation, and then multiple regressions, right? In this is usually the progression, the things we see in a statistics class. We sort of partition statistical tests according to our research question, right? And maybe, you know, you go through this and you end up studying t-test in one unit, ANOVA in another unit, and so on and so on. And you kind of feel everything is so fragmented, and there's no coherent structure, or, you know, there's no overarching narrative. And this is what everyone sort of feels when they take statistics. And that feeling is justified because this is what we do. But what I'm going to do is going to be slightly different. I'm going to take a step back and tell you why maybe there's a better way to learn stats. And that way is to look at all of these tests as one big thing. And if we can learn this thing right, if we know this thing well enough, not in terms of, you know, mathematical calculation, not in terms of, you know, solving equations, but if we get the basics right, we will probably have an easier time learning stats, and maybe we will enjoy stats a bit more. Okay, so just so you know, I am going to go through one example, and this example you saw last week. I'm going to repeat this example just to emphasize how it's like in a usual statistics class. Okay, we saw this example last week, but let me repeat again. So suppose your family runs a private school, right? And you have 500 students in your school. Okay, and one thing you notice with your students is their discrimination ability. You kind of feel that they have trouble discriminating minimal pairs, right? So if you say, is it pair, is it pair? And they have trouble distinguishing ber from per, right? This is the kind of things we do in English classes, right? So suppose you notice, you see this problem, and you want to try and fix this. So you decide to run a perceptual training experiment, right? This is an example, right? Let me walk you through this. Let's say you're going to bring your students in, train them over 3 sessions, and you have 30 participants in the experimental group, the group that receives training. And say you also have 30 participants who do not, 30 participants who do not get any kind of treatment, right? They are unfortunate. They don't get any training whatsoever. Okay. And after this training, you have participants listen to a bunch of new sounds. And for each one, for each trial, they have to design which word they hear. So they listen to the word, say bear, and they see the word bear and pear, and they have got to design which one they hear. They answer by pressing the keyboard, right? They answer 1 or 2, right? Pressing the keyboard. And you measure the reaction time in milliseconds, and you take this reaction time as an outcome variable, okay? So this is a stylized kind of research question that we often see. Okay, and let's say this is the data we have. Let's say this is what we have for our data. We have reaction time from an experimental group. We have reaction time from a control group. Okay, and this is our observation 1, right? This is observation 2, observation 3, so on and so forth. Okay, this is what we have for experimental group, control group. We also do some descriptive stats, and this is the average for the experimental group, about 500 milliseconds, and the control group about 550 milliseconds. Let's say this is what we have, right? So from this research, let's say from this research, what you want to do, what you want to find out, right? You care about the effect of training. Let's say you care about the effect of training. You want to find out how much can the training improve your students. So the effect of training in this experiment, you quantify it in milliseconds, right? You quantify it in milliseconds, the improvement we see. So you have the data here, and you try to figure out what's the true effect, what's the effect of training on reaction time. And we talked about this last week a little bit. This is the issue of point estimation, right? We try to use our data to estimate, to find out something about the parameters, about the population. So this is point estimation. We want to learn about the effect of training. Another kind of thing, right? Another thing you can do is this bracket here, and this is significance testing. You can ask, right? You can ask if the effect you see, right? That 50 millisecond difference you see between the two groups, if that effect is consistent with the null hypothesis, right? And this is significant testing. So you set up your research this way. You collect data, and these are two things you often do, or you hope to do in your research. If you have this data with you, right, you go into a statistics class. The professor may say, oh, this is a 2-sample t-test kind of research question. You are going to use a 2-sample t-test. If you have trouble figuring out what t-test is, just listen along right? I'm not gonna try to confuse you with a lot of math here, but just so you know, if you have this kind of research, right? If you have this design, if you happen to collect this sort of data in a usual statistics class, this example, this stylized experiment would belong to a t-test unit, and you will learn about two sample t-tests. And usually when you study t-test, what you have to do is to compare the mean difference against the null hypothesis. And t-test is often taught with this goal in mind. You just want to check if the difference is part of the null, if it is not, right? And in a lot of times, we never talk about this. We don't really say, yeah, what's the effect? How much improvement do we see? How much improvement does the experimental group get? Right? You go into a statistics class, you learn about two sample t-tests, and then what you do is to reject the null. And when you reject the null, you may also learn how to write this up. And usually people would write this kind of analysis up as, say, the experimental group was significantly better than the control group. And then you provide, for example, you say the experimental group was significantly better than the control group, right? And then you say, oh, and then you say T with some number here. I'm not going to go into detail. And then you report the p-value. And you report the p-value. This is what you usually see in statistics, right? You learn to report this kind of analysis. And you say experimental group was significantly better. I said earlier, right? I said you can still stick with this kind of analysis. I'm sorry, you can still stick with this interpretation. This write-up, I feel that this write-up is sort of okay. What you need to know, though, is that the word significant, in this context, when you use it, the word significant here does not mean that the experimental group was way better than the control group. Significant in this sense means that it is significantly different from the null hypothesis, from the null distribution, right? That's the word significant in this context. I don't feel personally against you writing this one out, but just so you know, because this is now the kind of things we do in the literature, right? But just so you know that the word significant is, the word significant means something totally different in the context of significant testing. The main point here being that you have this sort of data, and in a statistics class, you see this data with two sample t-tests, right? Well, if we happen to have another group, let's say we add the third group, right? We no longer have just an experimental group and control group. Let's say we have another group. And now t-test is no longer okay. You can't use t-test anymore because the two sample t-tests needs you to have two groups. You can only compare two groups and things like that. So you need to learn a new kind of test. You need to learn ANOVA. And then ANOVA comes with a different kinds of assumption. The name ANOVA is analysis of variance. So it is a different kind of, it is a slightly different analysis. And it has a different set of assumptions. So you need to relearn everything again. So in a statistics class, every unit is a painful experience. You start out with t-test, you try to memorize everything. You think you've got everything down. Time's up, move on to ANOVA. You have to relearn everything, or you need to learn everything again. Remember, try to memorize everything again. Now that you think you've got everything, the instructor moves on to another one, right? The whole process becomes super tiring, right? And I feel your pain. I don't like that kind of experience either. And so that's why I think maybe, if we start off with something that looks on paper, something that looks more difficult, but if we can get this one down, if we know where to start, and if we start off from this point, a lot of these tests will become much, much simpler to learn. And the bad thing, when you learn t-test, when you learn ANOVA piecemeal, one by one, over the course of the course, you become more and more inclined to look at just p-value, right? Because that's probably the only thing that all of these tests share. T-test, you have to look at p-value. ANOVA, there's p-value. You move on to another thing, there's p-value, things like that. And some other things change. And this p-value stays constant. And maybe this is the reason why people focus so much on the p-value, because it's the only thing that doesn't change from one test to another. For most people, that's what they feel, right? So I think if you are thinking about learning stats, if you want to brush up on your stats, if you want to try and relearn stats, I think the first place to start is to look at the linear model. And today I'll tell you a little bit about linear model just to get you started. There are some benefits to learning this thing, right? And applying it to other contexts, because you can learn a linear model as a single cohesive unit rather than learning t-test, Kruskal-Wallis test, correlation, Kendall-Tall, and things like that. There are a lot of names, right? If we can start with linear model and we get the basics right, whatever test that's thrown at you, it will become much, much easier to process. And believe it or not, we have actually nailed the first part of linear model, the one that we talked about, data generating process. When I told you this one comes from what, this one comes from what kind of distribution, that's actually the first part of learning about statistical modeling. So we have done something already that will be useful for your future. Finally, you thought, right? Finally, you thought, after 5.5 hours, I got to learn something useful. If you feel that, this is like, what's the point of this? I hear you. That's why I said, last week at the beginning of the class, I'm looking for a better narrative to teach stats. I'm not claiming that I am an expert in statistics, right? There are, other people are way, way smarter than me. And I've learned a lot from them. And they all say the same thing. They say start with linear modeling, understanding the basics here, and the rest will fall into place. Okay, now, enough said about this rambling thing. What is a linear model, right? What is a linear model? In plain English, it is a statistical engine. And what this engine does is that it relates an outcome variable to explanatory variables or predictors. If you read multiple regression, things like that, you see the word predictors. I sort of use both of them interchangeably. So a linear model is an engine, and what it does, it relates an outcome to a set of explanatory variables. The purpose of this engine is very simple. It wants to tell us how a change in the value of the predictor, a change in the value of the predictor, how that change affects the value of the outcome. So you can say that the change in predictor X improve Y, increase Y, or decrease Y, right? And does that change differ from 0? So if you start to feel into this one, right? Let's try and figure out how we can build a very simple model, or get the basics before our class wraps up. And to build a linear model is statistical modeling of any kind, right? A multiple regression model or multi-level model, things like that. It all starts off from this simple assumption. And the first one that I said, we have talked about this time and again. We look at our outcome variable, and we ask ourselves, we've got to make some assumption. We say, where is this outcome variable from? And I've used this again and again, right? Let's make this assumption that our scores are normally distributed, right? They come from a normal distribution. Now that we know they come from this distribution, there are two things we care about. Because if we know these two things, right? If we know these two things, we can describe the look of the distribution. If we know these two things, we can say, oh, the distribution looks like this. Or the distribution looks like this. Sorry. The color doesn't help. Right? If you feel brave, if you say, wow, I have a firm basis now, I'm going to go open any statistics textbook. I'm going to go right into regression model. If you feel brave tonight, you open some textbook, you may see this word standard deviation. When people talk about statistical modeling, standard deviation is sort of used to mean error. Just so you know, right? It captures the idea of error, and we can sort of see that from the distribution. We know where the center is, right? We know where the center is. The distance from the center, right? The distance from the center is kind of an error in our model. Okay, if you have trouble following along, that's okay. All right. I just want to point this one out, that standard error in statistical modeling sense tells you how much error there is in the data, because what we care about, we want to try and find the center, right? We want to find where this is, where this center is, right? So standard deviation somehow also captures this idea of an error in the model. But that's an aside. The main point here is we have an outcome. We make assumption about how it is, how this outcome variable is distributed, right? Then we want, because we care about this thing, the center. The next part of any model is to relate this one. See here, right? We relate this to a set of an outcome variable, sorry, to a set of explanatory variable. If you have trouble understanding this, that's okay, right? It means you are putting effort into this. So in plain English, what we do when we construct models, when we build models, when we try to use our model to learn about things, right? In plain English, what we actually just did was to say that scores can be learned from a combination of predictors. We say that scores can be learned from a combination of predictors. Or explanatory variables, okay? The whole idea behind linear modeling turns out this whole thing, we went through it in high school. If you are in some kind of science or math program, a science or math track in high school, if you went through that, right, or even a French English track in high school, we all learned a bit about linear algebra in high school, and the basic idea is the same. So let me walk you through. You don't need to remember all the equations and things like that. Let me walk you through the basic idea in a visual representation. This whole linear modeling thing, what we actually care about we want to express the relationships. We want to capture the relationship between a variable, one variable, let's call x, right? And this is often a predictor. Let's take just two variables here, okay? Just two variables. What we care about is to express this relationship. We want to find out how these two things pan together. So on one side, on one axis, we have one variable, right? On the other axis, we have the other variable. We call it y, okay? And this is, let's say, outcome, right? Again, let's stick with these two variables. It's easier to understand with two variables. With more variables, things get complicated. The idea is the same. We try to express the relationship between the two variables by building a two-dimensional pane, right?
And we say, okay, now that we have two variables, predictor on one axis, outcome on the other, we are trying to draw a line. We are trying to draw a line that represents the relationship between these two variables. This line will be a straight linear line. There is another kind of modeling, which is not about linear modeling. It's about a different kind of relationship, right? But for most of the things we do in TESOL and applied linguistics, a linear relationship is a reasonable assumption. And that's why we talk about a linear relationship. Just so you know, there are other kinds of relationship, right? But this one is probably one of the most common ones. Now, we have two variables. We say we are going to draw a line that represents the relationship between these two variables. In order to draw these lines, in reality, there will be data points, okay? I don't put them here, right? Let's make it simple. There is no data points here, all right? And I want to draw a line that represents the two. And in order for me to draw this line as correctly as possible, I need to have two things, right? I need to have two things. And this is what the model asks. The first thing is this point. Where does the line start? I want to pinpoint the location where the line takes off. This point is called the intercept. My handwriting is ugly now. I want this point. I need this point first, the intercept. This is the point where x equals 0. So if we write it out as an equation, just say into variable relationship, right? When x equals 0, this is when b1 times 0, and you get a mu equals to the intercept. I'll have an example to show you what this actually represents in an actual analysis. But for now, this is the point. The first thing we need to build our model, we need an intercept where this line takes off, right? And this is the point where x equals 0. But this is not enough. This is not enough. Another thing we need to know how steep the line should be, right? We want to know how steep this one should be. This steep, or this steep, or maybe there's 0 steep, right? The steepness is 0 or something like that. This is what we want to find out. This is the second thing. And this second thing is called a slope. And when you think of a slope, what is it? A slope tells us as you move one point up on the predictor scale, as you move one point up on the predictor scale, how much change can you see on the outcome scale. This is what a slope tells us. Now that we have these two information, these 2 points, these 2 things, we can draw a line, right? We can draw a line that best represents our modeling world. This is the basic of linear modeling. And quickly, very quickly, we can think of t-test, ANOVA, as some kind of linear models too. We can think of our control group, right? And this is actually what SPSS or any other program does. Behind the scene, the groups that we have, control group, experimental group, when you run a statistical analysis behind the scene, control and experiment are coded as, when we have 2 groups, they are coded as 0 and 1. And so we can line this one up with a linear model. We can also ask how much change occurred as you move from this group, the center of this group, to the center of this group, right? And this line sort of gives you an idea that we can sort of think of t-test as some kind of regression, as some kind of linear modeling. The only thing we want to find out, right? The thing we are interested in is the change here, the slope of the line here. If you are confused, that's okay, all right? But take my word, t-test, ANOVA, if you have SPSS with you, open it up, you can see where t-test and ANOVA are embedded under. T-test and ANOVA are embedded under the menu general linear model. So with that hierarchy, you can also see in the SPSS program, t-test, ANOVA are part of the general linear model. It's actually, everything is linear modeling. But anyway, because we are about to run out of time, and why am I presenting this to you, right? Of course, not only in terms of instructional value. If you learn one, you can master a few other things, and it will put you in good stead. But the reason I'm showing this to you right now is that if we think of everything as a linear model, and we use, for example, if you use R to run your statistical analysis, you can choose to run it with a t-test, or you can choose to run it with a linear model. What you get when you conceive things as being a linear model, you get more information. You get some useful information that you don't usually get when you just run t-test. So there's a practical reason behind that too. But let me show you what I meant by that. And let me flash that one, flash this one out again, right? Remember our group, the mean score for the experimental group is about 500 milliseconds. So that's like half a second, right? And the control group about 550. Okay, this is basic stats. So if we, let's see if I can zoom this one in. Okay, good. Let's say you run this with R, and you run it with a t-test command, right? This is what you get. If you run it with a linear regression on this side, this is what you get. If you don't know what R is, it's a statistical program. It's a programming language that's useful for statistical analysis. It's different from SPSS because, you know, in SPSS you have a user interface. You can click button, you can click this and this and that. You can drag and drop things. In R, you need to write code, but you know, codes are not difficult to learn. And R can do a few other things as well. But that's beside the point. The point here is if we run t-test or linear regression, we get the same results. And the purpose of this slide, this page, I want to show you that you actually get the same results regardless of whether you run a t-test or a linear regression. And this is a good sign that the two kind of tests that we sort of think they are different, this is a good sign that they are actually the same. So I'm not gonna, you know, unfortunately we will not have time to go and try and interpret this, but what I want to show you is this. Remember when I wrote this one down, right? Intercept is, we usually write alpha for the intercept and beta for the slope, okay? If you have more than one variable, more than one explanatory variable, you have B2, B3, and B4, right? Beta second, beta 2, beta 3, and beta 4, and so on and so forth. Behind the scene, very quickly behind the scene, look at this one. They are actually the same. And so behind the scene, the control group is coded as 0. And so here, the intercept becomes the mean of the control group. And the experimental group, what we see here, right, is minus 50. If we solve this equation, see what we get. We have this might be a bit too much, but stay with me. So 5.5 plus 50 times 1. 1 stands in for the experimental group. If you solve this, you get 545 minus 50, and you go down to 495. And 495 is what? And you get the p-value, sorry, the t, the exact same t right here. So why am I presenting this? I think, first of all, it's much more useful to learn about linear regression. If you want to be on the right track, it's much better to start with this. It is also useful because you can sort of capture, you can sort of think about the effect when you run a t-test, what people usually do when they run a t-test, they only care about this. And remember, we talked about the two sides, the two things you can get. The first one is the point estimate, right? The effect of this training. This is what you want to quantify. How meaningful is that, right? How useful is that? And another thing is that effect different from zero, right? When you run a t-test, what you only get in the output is basically the p-value, right? But if you take some investment and you start learning some linear modeling, you can see the two things. You can sort of see the estimate of the effect, and you can also see the p-value. I think this is what I like about, trying to learn things once, and you can sort of grab a few things along the way. Okay. And this is the last slide. We can now celebrate, right? Let me wrap this up. In most of the things we do, we express the relationship between an outcome and explanatory variables, typo there, sorry, between outcome and explanatory variables as a linear one. T-test and overcorrelation, we can express them as a linear model. So, if you want to learn stats, start with linear modeling, right? That will be a useful place to start. And if you are thinking, well, where should I go and find out more about this? I'm sending you guys this link. You can go to this page. This will be a good starting point. And from there, if you have trouble, the page, toward the end of the page, this guy gives more useful resources. So, play along. And I think that's it for me. I am able to wrap class before the end of our time. Okay, I think I can, yes, I'm going to give this one back to Oat.
Okay, thank you so much, Ajahn. ขอบคุณมากๆครับ Thank you so much. So we have about like 10 minutes. So do you have any questions? Anyone would like to ask?
I think everyone is tired of me now.
No, I think the more we understand, the more we learn, the better we understand the concept behind a p-value.
Can I just say one thing?
Yes, please.
I think my personal take on this, I try to make statistics fun. I try to make my class as fun as I can. And everyone should enjoy stats. But when it comes to the content, when it comes to the materials, don't take it lightly. I encourage everyone to study stats and take it seriously, because this is not about TESOL, this is not about applied linguistics. Think about this. When people talk about, the world today is about big data and things like that, right? Big data requires stats. If you are tired of TESOL, if you're tired of applied linguistics, you feel like, I don't want to do this anymore. Statistics can actually give you another alternative. It can be a good career opportunity. And some people may not have a strong background in stats, right? But with some effort and some learning, everyone can understand the basics, right? Everyone can understand the basics. So don't give up. If I make you feel depressed, just hate me, don't hate the subject, all right?
No. Well, you're so kind. Thank you very much. So I think we have one question from Pisangwon. How can we report differently from previous style of writing in paper as p-value less than 0.05?
I think the easiest answer would be, you know, like I said, stick with the same kind of analysis, stick with the same kind of write-up, right? Let's say group A was significantly better than group B or things like that, right? A more cumbersome way is to say the mean difference, but this will a caveat here. The problem with this, what I'm about to tell you, it will probably make people confused, but a more correct way to report it is to say the mean difference between group A and group B was not significantly different, or was not significant, sorry, the mean difference between group A and group B was not significant, or something like that. That would be slightly more appropriate, maybe. That would be a better version, but that's why I said it will probably trip people off, because everyone is so used to group A was significantly better than group B, things like that. You can stick with that report, but if you have a chance to explain your research, pepper it with more information, right? When you reject the null, tell them what does it mean. That's something we can do at this point in time for us, for each and every one of us, right? Because of course, if you try to break the norm, right? If you sort of stay away from this convention, people will be like, what are you trying to do? You don't understand stats, even if your understanding is okay, right? So that's a caveat.
Okay, well, thank you very much. So, any other question from Ajahn Dongkamon or Ajahn Sontaya or our TEFL friends? No? Okay, well, in that case, let me close this up. And I was just, on behalf of the TEFL program, I would like to say thank you very much, Ajahn Sakol, Suethanapornkul, for giving us this insightful lecture on the getting the basics right, clarifying doubts about statistics. And your lectures are very, very thorough, detailed, but still, approachable and also comprehensible. Thank you very much, Ajahn.
ขอบคุณครับ
ขอบคุณครับ Thank you so much everyone for joining this. And again, we have another session from Ajahn Modi on Friday, and that's open for the public. So I hope if you already register, I'll see you on Friday again from 10 to noon. So thank you again, everyone. ขอบคุณอาจารย์อีกครั้งครับ สวัสดีครับ
ขอบคุณครับ
ครับผม อาจารย์ขอบคุณอีกครั้งครับ